In this video, we continue our discussion on model optimization. We focus on situations that put some constraints on the solution we are looking for. The problem we discuss in this video is that of constrained optimization, where we have an objective function but also some constraints given in the form of equalities. And we only discuss here the case where all these functions are differentiable. This is the case that is most often found in practice, and we can apply to it techniques based on calculus as we have done in previous videos. The unconstrained optimization was in some sense simple because it only has one goal: to optimize the objective function. Constrained optimization is more difficult because it has a potential conflict of requirements: the optimization of the objective function and, at the same time, the feasibility of the optimum. There are many approaches for this kind of problems, and we only focus here on one based on merit functions. So we will consider here problems of minimization. Minimize f of x subject to the constraint g of x equals b. This is not a big issue. If we had a problem of maximization, very similar considerations would be applied. The approach in this case is going to be to replace the constraint problem with an unconstrained problem whose solution is an approximation of the solution of the original problem. That a point x0 is an approximation has two meanings here. On one hand, x0 is an approximation of a minimum point of f, and on the other hand, x0 is an approximation of a solution of equation g of x equals b. And then we will solve the unconstrained problem as we discussed earlier. There is no unique way in which to introduce a merit function. Examples for the problem to minimize f of x subject to some constraint g of x equals b could be some quadratic penalty function, which is, for example, f of x, which is to be minimized, plus something like g of x minus b squared divided by 2 times some constant mu. And this has to do with considerations related to the Euclidean distance between g of x and b. Or there could be something based on a so-called Lagrange multiplier merit function, which is again f of x, which is to be minimized, plus the deviation of gx from b, which is the module gx minus b, and sometimes we might even multiply that with some constant lambda to make it stronger in this merit function. The intuition that we should have when choosing a merit function is to estimate where lies the major effort in solving the original problem, in finding the optimum or in satisfying the constraint. And so we will introduce a smaller or maybe a larger term based on that constraint. No guarantee that a solution to the merit function will be a good approximation of the solution to the original problem, and in fact we may need to iterate several times. So here is an example. Let's say that we want to minimize this function f, now shown on the screen, such that 2x1 plus 4x2 equals 24. And we can introduce a merit function as we discussed before. For example, we can introduce this L of x1, x2, and some constant lambda to be f of x1, x2 plus lambda times 2x1 plus 4x2 minus 24. And so this is a good merit function because we want to minimize this, but we also want to stay as close as possible to satisfying this constraint. So this is equal to 27 over x1 plus 0.25 x1 plus 20 over x2 plus 0.1 times x2 plus lambda times 2x1 plus 4x2 minus 24. To minimize L, we can calculate the partial derivatives of L with respect to each of x1, x2, and lambda. So we are going to get a system of equations like this. Partial derivative of dl with respect to x1 is minus 27 over x1 squared plus 0.25 plus 2 lambda, and we set this to 0. The partial derivative of L with respect to x2 is minus 20 over x2 squared plus 0.1 plus 4 lambda, and we set this also to be 0. And the partial derivative of L with respect to lambda is 2x1 plus 4x2 minus 24, and we set this to be 0 as well. We can calculate numerically the solution with some standard software, and we will find out that the solution is the following. x1 equals 5.09, x2 is 3.45, and lambda is 0.34. And for these values, f of x1, x2, and lambda will be 12.71, and for these particular values we will even find out that 2x1 plus 4x2 is about 24. And if we do some simulations now and check what's the value of f for smaller and for larger values of x1 and x2, we are going to find out that if we obey the constraints 2x1 plus 4x2 equals 24, we will get always larger values. So that shows that we got a minimum point.